I think all our regulars are here, so I'm going to get started. If anybody comes in late, they can always look at the video. All right, first of all, good morning. Hopefully you're ready for a nice, hot, steamy day of chemistry with your host, Dr. White. It's already 80 out there this morning. It's going to be a steamer, but I'm going to keep it real cool. Uh-oh, bad humor, look out. All right, today's game plan is one, I better tell you, I sent out the password for test 3. You have until tomorrow, 9 a.m. to upload it to Blackboard, and please do that. I had a good fun with the password. If you've seen it, the password is all lowercase, as I said in my email, and please do it. I'll check my email from time to time in case you have a question. Email me, because in my class there's no such thing as a dumb question, including on tests. I gotta have some tea. Oh, is that good? All right, that's out of the way. Another thing I should tell you, if it's July and you're taking my course, Thursdays are test days. You'll hate Thursdays in July because of Dr. White, but gets the job done. Next Thursday will be test 4. Yes, I'll finish that. And because of that, over the next couple of days, I will post the points breakdown for test number 4. It will cover chemical equilibrium, which I'll finish today, and acids and bases, which I'll finish probably on Monday. On Monday, I will go through the equilibrium problem set. Sometime today or tomorrow, I'll post the acid-base problem set. But on Monday, I'll go through the equilibrium problem set along with other stuff. All right, today, I'm going to finish up the equilibrium chapter. Then I'll go through the great lab I wrote. Modest, aren't I? No. But anyways, I think you'll enjoy it. And then I'll continue on if we have time with acids and bases. So I better get started because we got a lot to do. Oh, that's not what I want. Here we go. Oh, by the way, warning, warning, you're going to be laughing hard when you hear Dr. White's north side of Chicago French accent. In other words, I'm going to butcher somebody's name badly. Over the years, I've had students who are from either France or from French colonies, what were colonies in Africa, and they've tried to correct me. They laugh hard when they hear me say it, and trust me, I've tried, but I still go back to my north side Chicago French accent. All right, let's get to work. I've talked about chemical equilibrium. Just a quick reminder. Chemical equilibrium was when you have a forward and reverse reaction, like here. The double arrow shows you it's an equilibrium. You should know that at equilibrium, the forward and reverse rate, how fast it goes in one direction or the other for an equilibrium is the same. I'll say it again. At equilibrium, when you have a chemical equilibrium, the forward rate of reaction and the reverse rate is the same. Yesterday, I taught you how to degenerate the equilibrium constant. I also talked about exothermic and endothermic reactions. If you missed it, go back and look at the videotape. I'm glad I'm putting those up, and I'm sure you are too. All right, I talked about how the size of the equilibrium constant, KEQ, tells you which side has the larger amount or concentration, products or reactants. When KEQ is larger than 1, there are going to be more products than reactants. When KEQ is much less than 1, in the equilibrium, if you measure the concentrations, there'll be more reactants than products. Just because the rate is the same going back and forth doesn't mean the concentrations are the same. At equilibrium, there'll be a certain amount of C to the power Y, D to the power Z, A to the power W, and X to the power B to the power X. And it will always be equal to a number at a certain temperature. That is a constant, means it stays the same. But all that tells you is there's a certain amount of A, B, C, and D, and K equilibrium tells you which one is predominant. Now, that's a quick review. Let's move on and look at the name. And here's my North Side Chicago accent. This is Le Chatelier's principle. Le Chatelier obviously was a French chemist. Tea break. Now, what is Le Chatelier's principle? Well, it deals with equilibrium reactions. And one way of saying it is when a chemical system at equilibrium is disturbed, the system shifts in the direction that minimizes that disturbance. Another way of saying that, if a stress, a change in condition, is applied to a system in equilibrium, the system will readjust, in other words, change the position of the equilibrium in the direction that best reduces the stress on it, on the chemical equilibrium. Now, what that really means is in real life, if you're at a party and somebody's bothering you, being really obnoxious, you're under stress. What do? Well, the easiest thing is go away from that person. That's Le Chatelier's principle. If you're uncomfortable about something, you're going to do something to make it less uncomfortable. That's Le Chatelier's principle. Let's look at how this applies to chemical equilibrium. Now, the first thing that you can put stress on is how much of a substance in the reaction is present, otherwise known as the concentration. Oh, see board. Dr. White has to get to work. Let's do a real simple equilibrium. Here we have the equilibrium sign. A plus B is in equilibrium with C plus D. Now, let's look at Le Chatelier's principle. All right, let's look at the first one. And the question is, what happens to the concentration of B and D, how much B and D are there, if you add more A? So at equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, certain amount of D. Now, if I were to take an eyedropper with a beaker of A, and in the reaction beaker, I put in more A, now there's more A. And because of Le Chatelier's principle, the reaction everybody says, oh no, I'm under stress. Why? There's more A than there should be. What do? Well, we use the Chatelier's principle. And the Chatelier's principle says, well, if there's too much A, how do we reduce the level of A? Well, the only way you can reduce a reaction or amount of a chemical in a reaction is by having it react with something else. And in this case, if I want to reduce the level of A has to react with B to make more C and D. What happens is when A reacts with B, this and this will be used up. It's called consume. Now, this sometimes is a concept students have a problem understanding. Let's talk about something simpler. Let's assume you have a blueberry pie. Dr. White loves blueberry pies, and cherry and apple too. French silk are the most dangerous, but let's stick with a blueberry pie. What if you eat a piece of that blueberry pie? Do you have the same amount of blueberry pie present, more or less? Well, if you ate a piece, you're going to have less because you started with a whole blueberry pie, you cut out a piece and ate it, and now you have less. What have you done? You've consumed some of the blueberry pie. So when two reagents react or reactants react, they're consumed and their concentration drops. So when you want something to decrease, you react it with another and it goes in the direction. So since there's more A, because we added it, there's too much. And how do we get rid of A to make it lower? We react it with B. So if we react A with B, what happens to the concentration of B? And I'll abbreviate it by first getting the right color. Since it's going to be reacting or consumed, it will decrease. Now, what happens to the concentration of D? I'm getting better at my concentration symbols. Well, if A and B are reacting to get rid of the excess A, when they react, A and B make more C and D because it's going this way. And therefore, we're going to make more C and more D. So what happens to the concentration, the amount of D? When you make more of it, guess what? It increases. So let's go over why this happens. Well, Chatelier's principle says an equilibrium under stress shifts in the direction to remove the stress. One of the things at equilibrium, there's a certain amount of each reactant and product present at equilibrium. When you add more, it's going to say, oh, woe is me. Didn't you know molecules could talk? They can, not really, but it's nice to think they could. A and B, you've added more A, and everybody looks at this equilibrium and says, oh no, we've got too much A. We've got to reduce that. I'm under stress. And therefore, how can you reduce the excess amount of A? It reacts with B to make more C and D. And that's how we know what happens to the concentrations. If you react A with B, the amount of A will decrease. If you react A and B, it makes more C and D, and therefore the amount you make, if you're going to make more, what you had, you're going to have more, and that's why the concentration, remember in a bracket that's moles per liter, a shorthand is saying concentration will increase. Ooh, this is fun. Let's do another one. What happens to the concentration of B and D if you remove some C? And I'll explain later today how you can do that in real life. And Dr. White has, both in the lab and in chemical plants. Why don't you think about it for a second? I'll give you a couple more seconds while I clean up the screen here. Also going to sneak in a tea break. All right, time's up. Put down your computers. Anyways, it's awful humor Thursday. At equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, certain amount of D. If I remove some C, I mean, what happens? Oh no, there's less C than there should be. And now I'm under stress. How do I get rid of that stress? Somehow I've got to replace some of the C that has been removed. Well, here's our reaction. And the only way you can make more C is by reacting A and B. So if I take A and B and react it, I'll make more C. Well, if I react A and B, these are consumed because they're used to make C and D. So now I look at that and say, well, if I consume some B, because I'm making more C to replace what was taken away, what happens to the concentration of B? Well, if it's consumed, it's decreased or decreases. And on a test, you can either put an arrow down or to write out the word decrease or gets lower or other synonyms for decrease. Ooh, Dr. White used a fancy word, synonym. Now, the other question is, what happens to the concentration of D? Well, if I need to make more C by reacting A and B to go this way, if I make more C, I'm going to make more D. If I make more D, it will increase. Oh, let's do another one. These are fun. And I'll let you try this one all on your own. What happened for this equilibrium? What happens to the concentration of B and D if you add more C? You try it now. Use the Chattelier's Principle. If any of you speak French, you can laugh real hard at my North Side Chicago accent, French accent. I were in a class now, I'd look around and say, if you're done, look up and smile. I see people are thinking. If you're done, give me a thumbs up. It's a little tough to understand at first. Remember, when you're done, give me a thumbs up. I'll come back in 10 minutes. No, I won't. Everybody done? Okay, let's go ahead and do this anyways, because I got stuff I want to get through. I don't think you want to be here till midnight. All right, let's look at this. What have we done? At equilibrium, there's a certain amount of A, certain amount of B, certain amount of C and D, meaning the concentration. What we did was add more C. Now the equilibrium looks and says, oh no, we have too much C. We're under stress. How do we get rid of some of the excess C? Well, there's only one way to get rid of something. Have it react with something and be consumed. Therefore, if C reacts with D to go this way, remember this is a reverse reaction and equilibrium can go both ways, C and D react. When that happens, C is consumed, used up, and D is consumed. So immediately I can write down, if something is consumed or reacted, the concentration will go down, decrease. Now, when you react something, what do? If C reacts with D, you're going to make more A and B. When you make more of something, you have more. So therefore, the concentration of B increases. And that's the Chattelier's principle. A equilibrium under stress shifts to the direction to remove the stress. Now, that was how the effect of concentration changes on the equilibrium. Let's look at the effects of temperature on the equilibrium. And I'll be talking about exothermic reactions and endothermic. See board. Now, before we look at the board, I'm going to write something down here. By the way, RX is shorthand in chemistry for reaction. Dr. White's lazy. Now, when we talk about exothermic reaction, that's a reaction that gives off heat. This one, you have to add heat to make it work. Now, in the lab and also in a chemical plant, if you put a reaction in hot water, also known as boiling water, that adds heat. Now, the other thing is, if you have a beaker with ice and water, we call that an ice bath. If you're putting a reaction in an ice bath, it's in a test tube, and you put in a beaker of ice and water, it's cold, and what does that do? It removes heat. Haven't done it all day, I better do it. Thumbs up, people. Can you see exothermic reaction? Thank you. All right. Now, here we have an exothermic reaction. How do we know that? Because it gives off heat. Now, normally you think of the equilibrium constant, always, as concentrations. But when you think about the Chatelier's principle, heat has a role. Because when you're in an equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, D, and there's a certain amount of heat. And sometime in your future, if you happen to see it, instead of A and B, I'll probably have chemicals there, formulas. But if you see this equilibrium and 3 points each, what happens and when you have brackets and a chemical, this is concentration of A and the concentration of C if you put the reaction in boiling water. Well, let's figure out, what does boiling water do? It adds heat. At equilibrium, there was a certain amount of heat. Now you've added heat by putting it in the boiling water, and the equilibrium says to itself, oh no, we've got too much heat. We're under stress. How do we get rid of the excess heat? Well, there's only one way. If C reacts with D, it also reacts with the heat to go in this direction. And that will reduce the amount of heat, reduce the stress with Chatelier's principle. So if C and D react with heat, what happens to the concentration of C? It's being consumed. Oops, wrong color. When something is consumed, you lose it or it gets decreased. Now, what happens to the concentration of A? Well, if C and D are reacting with heat going this direction, what happens? You make more A and B. Well, if you make more of something, you're going to have more of it. Therefore, what happens to the concentration of A? It increases. Or you can put increase, goes up, gets bigger. Those are all fancy word times synonyms. Now, let me ask you to try one. Let me make some room here. Wow, just like in a classroom, I'm erasing the whiteboard. And why don't you try this one on your own? Dr. White will share the fun. What happens to the concentrations of A and C if you put the reaction in an ice bath? In case you forgot, ice bath removes heat. Psst, ice bath removes heat. Remember, when you're done, smile or give me a thumbs up. Oh, I see some people are getting the hang of this. And that's a good thing. If you're having trouble, sometimes it takes a little while to get your head wrapped around the Chattelier's Principle. I like my North Side Chicago French accent. All right, anybody need more time? Going once, twice? All right, let's do this. Now, what have we done? We've put this in an ice bath. And what does an ice bath do? Doesn't help me spell. An ice bath removes heat. So at equilibrium, oh no, D ran away. It came back. At equilibrium, there was a certain amount of A, B, C, D, and heat. We've removed heat. So the equilibrium looks at itself and says, oh no, we don't have enough heat. Someone stole some of our heat. Well, what does it want to do? It doesn't have the amount of heat it should. So how do you make more heat? A and B react to make more heat. Now, when A and B react, A and B are consumed. When you consume something, you have less of something. Therefore, since you consume some of A to make the heat, because there wasn't enough, we took some out, the amount of A concentration will decrease. Now, when A and B react to make more heat, what happens to the concentration of C? Well, if A and B react to make more heat, they're also going to make more C and D. Therefore, the concentration of C will increase. And that's how you use the Chattelier's principle for an exothermic reaction. Here we have an equilibrium. It's endothermic because we have to add heat. It's on the left side. And that's the convention for exo and endothermic. All right, I'm gonna let you have fun and then I'll do it. Here's the equilibrium. What happens to the concentration of E and H if you put the reaction in an ice bath? Remember, ice bath removes heat. You try this one. These are tough. You got to really use your mind and stretch it, but with a little practice, you'll get it. Remember, when you're done, smile or give me a thumbs up. All right, let's go ahead and do this. And I was telling me my internet connection was unstable. Let me just check. Everybody still see me or see my good? I'm back to being stable. All right, let's look at this. For an exothermic reaction, here's the equilibrium. Heat is here. When you put it in ice bath, what happens? You're removing heat. At equilibrium, there was a certain amount of heat, E, F, G, and H. And now you removed heat. And now the equilibrium says to itself, oh no, we don't have enough heat. We need more heat. How can it make more heat? Only one way. G and H react in this direction and they make more E, F, and heat. So if G and H react in this direction, we're making more heat. We also make more E and F. Therefore, when you make more of something, the concentration will increase. Now, how do we make more heat? We react G and H. What does that mean? They're consumed. They react together. When something is consumed, just like the blueberry pie, you have less. So therefore, what will happen to the concentration of H? Well, since it's reacting with G to make more heat, it will decrease. And that's what happens. Now, if I were to put this in hot water, boiling water, there'd be too much heat. And in order to get rid of the too much heat, the equilibrium would shift this way. Now, I've been speeding along through this. Good news, next week, I'll have plenty of time on Monday to go through this both in the problem set and go through some more examples like this in class, because we're at the part of the semester I can do that next week. What I'd like to do right now is talk about the lab you'll be doing today that's due next Tuesday. Let's take a look at this. This is available on D2L. And in this lab, let me just check with my thumbs up, people. Everybody, thank you. I don't even have to say. All right, we're talking about chemical reactions in Chattelier's principle. You know about a chemical equilibrium. Now, there are two types that you're going to be investigating in this lab. One is an exothermic equilibrium reaction, where the heat is on the right side. The other is an endothermic reaction, where the heat is on the left. Now, the two reactions, I'm going to give you this part. But look out, Dr. White's going Technicolor. You're going to have to figure out which side the heat is. How do you do that? By having fun putting the equilibrium under stress. And let's look at the first reaction or part of the lab. In this one, you're going to be using cobalt ion equilibrium. And if you take cobalt tetrachloride ions with water, it's an equilibrium with cobalt hexa, I said yeah, I was right, hexahydrate and chloride anions. Now, what you're going to be doing is first looking at the color. And depending which side is predominant, which has the most of either this or this, you'll know it's either pink or blue. If they're equal, it's going to be like a purple color. And the first thing you're going to do is add 2 milliliters of solution in a test tube, look at the color. After a couple minutes, you'll add 5 drops of deionized water, this, and look at the color after a couple minutes. The next one, you'll add 5 drops of 12 molar, you know what capital M is, HCl solution. HCl solution is a way of adding Cl minus, and you'll see what color the equilibrium shifts to. Then you're going to put the test tube in boiling water. Remember, that adds heat, and record it, and then you'll take it out and put it in an ice bath, and that removes heat. And then afterward, you'll put it in there. Here's the data for that reaction. You can see this in a YouTube video. Now, let me show you something that's important for this lab that I haven't done others. If you were in the lab, I'd be handing this out to you. Everybody see the help sheet? Thank you. And here's the equilibrium again. I think I got the colors right. I might have had it wrong in the basic lab, but I don't think so. When you add water, you're increasing this concentration. When you're adding the 12 molar HCl, you increase this. When you put it in boiling water, you add heat. And when you put it in an ice bath, you remove heat. Now, this is either an exothermic or an endothermic reaction. And what Dr. White didn't do was, is the heat on this side or is the heat on that side? You have to figure it out. Now, how do you do that? Don't tell anybody, I'm being nice, I'll ruin my image around here. But note, boiling water shifts the equilibrium to the side without heat. Ice bath shifts the equilibrium to the side with heat. So you can figure out by the color of the solution if it's exothermic or endothermic. Now, there's a part 2 because I wanted to make it interesting. And in part 2, here's the equilibrium reaction. Now, instead of color, on this side, if this is predominant or shifts, you'll see a solid. On this side is clear. So you can look at the test tube. If it's solid, you know it's going in this direction. Look out, he's going real fancy today. And if it's clear, that's an If it's clear, it's going in the red direction. So by looking at the test tube, by adding things and understanding the Chattelier's principle, you can determine, first of all, am I telling you the truth? And second of all, which side is the heat? Is the heat on this side or does it go on this side? Is this an endothermic or exothermic? I'm not going to tell. And you're going to do the same thing. In a test tube, you will be putting 2 milliliters of ammonium chloride equilibrium solution. That's this up here. This is ammonium chloride. And you'll record, is the solid present or not? Then you'll add some 5 drops of HCl, 12 molar HCl solution, which adds more chloride anion, this, and you'll see which way the equilibrium shifts, to the blue or the red. You know the Chattelier's principle, and you can figure that out. Next, you'll put it in boiling water and look, is there solid or not? Then you'll take it out and put it back in the ice bath, or in an ice bath, and look, is it clear or not? Now, the fun thing about this lab is 4 and 5, you can go back and forth as many times as you want. Watch this go clear or get a precipitate, which is called a solid. Now, for part 2, adding hydrochloric acid, you have this. There shouldn't be a 2 there. I don't know how that came about, but mistake by Dr. White. I was in a haste. But anyways, you add more chloride. When you put it in boiling water, yep, you add heat. Put it in ice bath, you remove heat. And don't forget, you're trying to figure out which side, this side or this side. Either here would be plus heat, or his side it would be plus heat. And this helps you out. Boiling water shifts the equilibrium to the side without heat. ice bath shifts the equilibrium to the side with heat. And that's what you're going to do. Now, I didn't look for a YouTube on this. If you find one, let me know, but that's not important. Now, and here again, I put the data, initial clear. When you add HCl, it's solid. When you put it in boiling water, it's clear. When you put it in ice bath, it's a solid. Now, here are the questions I asked, like in part 1, when you added water to the test tube, what color did the solution become? And use the Chatelier Principle to explain the reason for the color change. Same thing when you put it in an ice bath. And finally, write the equilibrium equation for part 1, and please include heat on one of the sides. In other words, is it exo or endothermic? And I do the same for part 2 questions. And that's the lab. If you have any questions about how to do this lab, this is one of the harder ones, so I shouldn't have said that. Now you'll think it's hard. But remember, Monday night, I will have my office hour. And remember, there's no such thing as a dumb question in my class or in the lab. Students take a while to figure that out when we're actually in the lab. I can ask questions about what? Sure. And so I'm always here to help you. Tea break. Boy, talking about equilibrium is thirsty work. All right. Here's the one I'm looking for. This quick, everybody see the exothermic, endothermic? Okay. Now, using equilibrium constants, I'm going to skip this. Solubility constant, I'm going to skip this. That means I'm done with chapter 15. I'm going to go a couple extra minutes today. Hang in there. It's for your good, not mine, because I'll do good on any test I give, but this will help you. Guess what time it is? It's new chapter time. Remember, on Monday, I'll go through the equilibrium problem set. But let's go into the new chapter. And this new chapter talks about probably the most important thing I can teach you this semester that you'll use in your daily life or maybe professional life is acids and bases. And the question is, remember, this is for test number 4 material, which will be a week from today. Now, what's an acid? What's a base? That's a hard question. And for many, many years, chemists couldn't properly answer that question. Late 1800s, a chemist called Arrhenius, switches off for this slide, came up with the Arrhenius theory of acids and bases. And an acid is a compound that in water produces H+, hydrogen ions. A base is a hydroxide-containing compound that in water produces hydroxide. Now, there's a problem with Arrhenius theory, and that is this only works if you're talking about water. And there's a lot of chemistry, including a lot Dr. White has done, that's never done in water, and it uses acids and bases. Well, that was a problem. Now, before we do go on, let's look at some key acids. You've already heard me talk about the switches on, you should know the structures. First one is hydrochloric acid, and that's the structure. Next one, sulfuric acid, H2SO4. And these are very important compounds in our daily life, meaning making things you use. You don't use them yourself personally. I take that back. Let me write down nitric acid. HCl is in your stomach. When they talk about stomach acid, they're really talking about hydrochloric acid. I always think it's one of the miracles in life that I and you have cells in our body that synthesize, that's the fancy word for make hydrochloric acid. Now, acetic acid, I won't ask you to learn the structure or formula, but here it is. And most of you have acetic acid in your house. No, I don't. Yes, you do. If you take about 4% acetic acid and about 96% water, mix it up, you get a homogeneous solution. We have a name for that. Vinegar. Any vinegar, rice wine, champagne, or any other apple cider vinegar, all is essentially acetic acid and water. But you should know hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid. Now, there's some key bases. Sodium hydroxide is a very important base. NaOH. Again, I'm going to go about 10 minutes over, maybe less. Hang in there. Potassium hydroxide is a base, KOH. Ammonia, which we've talked about, NH3 is a base, and something you have in your house or your parents do, sodium bicarbonate, which you also know is baking powder in the little red can if you buy Calmet. Also, there's a real bizarre yellow can called Gabler Girl, weird name Gabler Girl, and that's made in Indiana. So these are key bases you should know. Sodium hydroxide, NaOH, potassium hydroxide, KOH, ammonia, NH3, sodium bicarbonate, NaHCO3. Now, the problem with the Arrhenius theory was it doesn't work in non-aqueous solutions where you don't have water. Well, it turns out two chemists, Bronsted, another chemist, Laurie, at the same time, this is about 1910, 1920 era, independently came up with an acid-base theory. And because they both came up with it at the same time, we now call that the Bronsted-Laurie theory of acids and bases. And this you should know. Switch is on. If I could turn the switch that only goes up to 10, I've just turned it up to 1,000. What is a Bronsted-Laurie acid? It's any substance that can donate a proton, which we designate by H+. What is a Bronsted-Laurie acid? You should know. It's a proton donor, H+ donor. If I'm an acid, Bronsted-Laurie acid, I come up to you and say, here, take my proton. I'm an acid. Now, an acid is a Bronsted-Laurie acid is a proton donor. By the way, to this day, this is the most widely used theory of acids and bases, and I use it, and most chemists use it. There's others for other examples, but this is the key one. Now, what is a Bronsted-Lowry base? A Bronsted-Lowry base is any substance that can accept a proton from something else. So what is a Bronsted-Lowry base? You should know. That's a proton acceptor. Remember, a proton is H+. That's a hydrogen atom that's lost its one electron. So, Bronsted-Lowry base, proton acceptor. Bronsted-Lowry acid, proton donor. And you should know this. Now, in water, a proton immediately reacts with water to form what's called the hydronium ion. And this is important. And this is an important thing. It happens in your blood. It happens in your stomach. I guess you can say it happens in your mouth too. Everywhere there's water. Now, because Bronsted-Lowry you don't have to be in water. If we look at this is an acid. This is a base. How do we know this? This had a proton. Now it doesn't. So it gave up the proton. Where did it give the proton? To the ammonia, NH3. Notice it had 3 hydrogens, no charge. It has 4 hydrogens plus a charge. So this is donate, or donates H+. This accepts. H+. And that's how we use the Bronsted-Lowry theory of acids and base. Proton donor, acid, proton acceptor, base. And that's how you do that. I think this is a good time, because I don't want you got to take a test today. Bad, Dr. White. You can all give me a dirty look. That wasn't too dirty. But anyways, it's time for Dr. White to say goodbye. Bye. Gehen gesund. Be healthy. Don't forget, test number 3 is due tomorrow morning. I will be checking my email about every hour or 2 today. If you have any questions, don't forget, on Monday, I will be doing the equilibrium problem set, work on it, and I'll do more examples, and we'll continue on, and we'll finish Monday well in advance of Thursday's exam. Tuesday and Wednesday, I'll spend more time on acids and bases and go back to equilibrium again. So you'll be all set for test number 4 when it comes out. With that, bye. Stay cool and gehen gesund. Be healthy.